So talking for IAP Kerala or in Kerala is almost like homecoming for me. I am so familiar with the entire team. So with these few words, I'll just share my screen. Sorry, I just can't. Yes. So today's talk is going to be immunology as related to vaccinations. Well, open up any book on immunology, and what you find are diagrams like this. Strange capital letters which have no relationship to each other. Many words which I've never heard. Circles and squares of different colors. Arrows shooting off in different directions, making no sense to us. And our first contact with vaccinology is, oh my God, do I really have to learn about this? But immunology is at the very core essence of vaccinology. And almost every single parameter in the practice of vaccinology, be it interval between vaccines, can we give these vaccines together, and many other such issues are answered when you know about the immunology of vaccinations. So today, I will talk about a very simplified approach to immunology of vaccinations, and with a lot of emphasis on its application in day-to-day practice. Why you are doing this? What is the immunological basis for doing this? So first, let's get some definitions clear. We often talk about vaccinations and immunization almost in the same breath. Are they the same? Well, there are subtle differences. Vaccination is the art of introduction of a vaccine into the human body to elicit protection against a particular pathogen or disease. So vaccination is just introduction of the vaccine. On the other hand is immunization, whereby you induce protection against the disease by vaccination. So immunization follows vaccination. So there is a subtle difference between these two terms. So what is a vaccine? A vaccine is a complex biological preparation that safely imparts adaptive immunity against a particular pathogen or its subtypes on subsequent exposure. Please note, there are many qualifications for this statement. It's a complex biological preparation. It should safely impart adaptive immunity against a particular pathogen or its subtypes when there is a re-exposure. Now, when you look at the vaccine, it consists of the antigen, which is derived from the pathogen or nowadays synthetically produced. You have adjuvants to enhance the immunogenicity of the vaccine. You have stabilizers. See, vaccines undergo many processes: heating, thawing, cooling, freezing, storage, some temperature variations. The vaccine has to remain potent. That is the role of stabilizers. Multi-dose vials, which are going to be punctured many times, need a preservative to prevent bacterial contamination. And then ultimately you have some egg proteins, some antibiotics, some formaldehyde, which are the residuals of the manufacturing process. Of course, these are in very minuscule quantity, not really very important, except when you have allergies to vaccines, you have to look into these components of the vaccines. But if you look at the immunological response, of paramount importance are the antigen and the adjuvants. So as I said, it imparts adaptive immunity. So what are the types of immunity? We have adaptive and we have innate. Adaptive immunity, we have natural and artificial. Natural can be passive or active. Artificial also can be passive or active. A vaccine imparts adaptive, artificial, active immunity. But in modern vaccinology, there is a tendency to exploit innate immunity. So nowadays we are looking at vaccines where even the innate immunity is being looked at as a very potential target to get a good vaccine. Now, when a pathogen enters the body, there are three barriers. The first are the physiological and physical. You have the skin, you have the mucous membrane, cilia, the body temperature, you have the pH, you have secretions like the tears, you have the gastric juice, which to a great extent reduces the bacterial load. The next barrier is the innate immunity, and finally, we have the adaptive immunity. But when you look at a vaccine, you must remember that almost all vaccines that we use are parenterally administered vaccine. Whether it's a respiratory pathogen, whether it's a gastrointestinal pathogen, or a pathogen entering from the mucus of the genital tract, we are giving it parenterally. So the first barrier is skipped. So a vaccine involves innate and adaptive immunity. So first, let's look at innate immunity. The three or four main players are the dendritic cell, the macrophages, the B cells, and the natural killer cells. And how do they work? Of these, the dendritic cell is most paramount. Now, these dendritic cells are like policemen. They're patrolling all over the body, in the blood and in the tissues. The moment there is a pathogen which enters the body, they sense the danger because these antigen presenting cells have receptors called pattern recognition receptors. And these recognize pathogen associated molecular patterns on the pathogens. So pattern recognition receptors recognize pathogen associated molecular patterns. So what is PAMP? PAMPs are basically highly conserved molecules. They can be proteins, they can be carbohydrates or lipids. When I say highly conserved means they have been present almost since the time these organisms have evolved, and they continue to remain in all the types and subtypes. Example includes the lipopolysaccharides and the peptidoglycans of the gram-negative bacteria. Then we have the teichoic acids and the peptidoglycans of gram-positive. Mycobacteria have mycolic acids. Flagellin is a very important PAMP. Viral RNA and DNA are also very strong pathogen-associated molecular patterns. Now, what are these pattern recognition receptors? We have many of them. Some of them are membrane bound, like this TLR2 and TLR7. Some are cytoplasmic, like TLR9, 7, 3, 4, caspase, NOT2, etc. Basically, when a pathogen-associated molecular pattern combines with a pattern recognition receptor, it sends signals to the nucleus of the cell. It heightens the activity of the DNA with production of and secretion of antiviral interferons and many other cytokines. The end result is either the pathogens are killed or the cytokines produce a highly inflammatory atmosphere wherein more and more antigen presenting cells enter and fight the particular infection. So to summarize, innate immunity is rapid. It is non-specific. Whatever the antigen, it is the same type of molecular response, and there is no immune memory. A little qualification of this last word. So when we talk about innate immunity, it will remain complete if we don't talk about trained innate immunity, especially since the onset of the COVID pandemic. This particular terminology has gained very, very great importance. Now, when a pathogen enters the body, the innate immune response comes into play and starts producing cytokines. After a variable period of time, if a second exposure occurs to the same or an unrelated pathogen, what is found is that the cytokine response is 4 to 10 times that observed in the first phase. This is surprising because we expect the response to be the same every time. And why does this happen? Because of a process called epigenetic programming. Now, what is this epigenetic programming? You have modifications in the histone, DNA, a closed chromatin network becomes open, modulation of microRNA, and certain RNA expression is enhanced. As a result of which, these changes occur right in the hemopoietic precursor cells. If it was occurring only in the peripheral antigen presenting cells, the duration of this trained innate immunity would not have been more than a few weeks. But there is definite evidence to show that this trained innate immunity lasts for a very long period of time because these changes occur right in the stem cells. So trained innate immunity works against related and unrelated pathogens, and it lasts for a pretty long time. As far as the adaptive immune response is concerned, we all know it is mediated through either a cell-mediated response or a humoral response. A cell-mediated response is through CD4, CD8 and its products, cytokines, or a humoral response through B lymphocytes and which produce antibodies. But what we must remember is these are not watertight compartments. And the dendritic cell acts as a communication between the innate and the adaptive immune response. And now there is enough data to show that the innate immune response can affect the type of the adaptive immune response. So today, there is a tendency for using or stimulating the innate immune response when you want a particular type of adaptive immune response against a particular pathogen. Now, so in contrast to innate immune response, adaptive immune response is slow in onset, that was fairly rapid. It is antigen specific, that was antigen non-specific. Here, there is induction of immune memory, which was not there with the innate immune response. Now, let's look at the players in the adaptive immune response. We are mainly concerned with two cells, the B cells and the T cells. And in these two cells, we are mainly concerned with two specialized structures called the B cell receptor and the T cell receptors. The B cell receptor is an immunoglobulin molecule. As you all know, it has a heavy chain and the light chain, and each chain has a variable and a constant segment. Let us concentrate on this variable segment. There is a part of this variable segment which is called hypervariable segment. And what is its importance for us today? Because this entire variable segment is encoded by about 1,000 genes, but these 1,000 genes can generate almost 10 million antibodies. And how does that occur? That occurs by a process known as somatic recombination and mutation, which occurs in this hypervariable region, as a result of which there is virtually no known molecule, either biological origin or synthetic, to which the body cannot produce an immune response. That is the diversity of the human adaptive system. Moreover, it is postulated that the human immune system can respond to as many as 10,000 antigens at any one time. So what is that implication for us in our practice? The immune system can never be overwhelmed. You can give any number of vaccines at a particular time, and the body will be able to respond to each and every antigen that you deliver. Now, how does the adaptive immune response work? We said we have a humoral and a cell-mediated immune response. The humoral response works by production of antigen-specific antibodies. And these antibodies work by either neutralization, they coat the entire microorganism and do not allow its receptors to come into contact with the host cells, and these cells are phagocytized. Opsonization. Opsonins are certain proteins, Y-shaped proteins, which are produced in the spleen. These coat the microorganisms, and this end sends signals to the antigen-presenting cells that here is a microorganism, come and engulf it. And the third component is the complement. The complement may either function as an opsonin or it can directly kill cells. So What is the function of the humoral response? Early reduction of pathogen load and clearance of extracellular pathogens. Coming to the cell-mediated immune response, it is induced by T lymphocytes, which have two functions. One is supports antibody production, and secondly, it can directly kill cells which have been infected by viruses or protozoa or bacteria which are intracellular. So cell-mediated immune response is essential for clearance of intracellular pathogens that are present inside the cell. So what are the events once you give a vaccine? This little kid has now just received a shot. So what are the events that are going to happen? First, the antigen should be taken up by the antigen presenting cells, giving rise to an innate immune response. These antigen presenting cells then have to reach the draining lymph node where the immunological response occurs. Within the lymph node, the immunological processes are slightly different from polysaccharide antigen and protein antigens. And finally, generation of immune memory. Please remember, generation of immune memory is the very purpose of any vaccine. Short-term protection is not the purpose of vaccination. You have to generate immune memory so that you have fairly long-term protection. So let's take the first step, that is antigen uptake. Okay. Now, when a vaccine is administered, here we are talking about an intramuscular vaccine. The vaccine antigen has pathogen-associated molecular patterns which are recognized by the pattern recognition receptors. This was true for the older, unmodified, killed vaccines or live attenuated vaccines. But nowadays, we are getting highly purified antigens, subunit vaccines, acellular pertussis, where all the PAMPs have been removed to reduce the reactogenicity. So such vaccines need an adjuvant. The adjuvant function as a PAMP, and that reacts with the pattern recognition receptor and initiates the immune response. So what are the implications? Highly purified or synthetic antigens need adjuvants to elicit a protective immune response. And what is an adjuvant? A vaccine adjuvant are molecules or compounds that have an intrinsic immunomodulatory properties. And when it is administered with a vaccine, the immunological response is far superior to what is elicited when it is administered without an adjuvant, right? So adjuvants heighten the immune response of the vaccines. Adjuvants are of various types. You have those which help the antigen to remain at the site of deposition so that the antigen presenting cells can slowly absorb them, and these will not get washed away. Alum is a classical example. Some activate the pattern recognition receptors like the TLR. Covaxin has a TLR agonist as one of its adjuvant. Then we also know that there are certain intracellular structures called inflammasomes, and this is stimulated by alum. And finally, there are some adjuvants which enhance the presentation of the antigen to the class MSC molecules. Ultimately, why do we use adjuvants? We want to enhance the immune response. So you can use less quantity of antigen and produce a vaccine. So there is sparing of antigen, and this is specifically important when an antigen is either too expensive or is in very short supply. Cross-reactive immunity. You all know that Cervarix had ASO4, and as a result of which it had a lot of cross-reactive immunity against serotypes which are not present in the vaccine. We know that influenza vaccine doesn't work very well in the immunocompromised and even in the elderly. So adjuvants are added to it so that you get a better response in the elderly. And finally, when to want to skew the immune response in a particular direction, like for viral vaccines, you want a type 1, a CMI, cell-mediated immune response. There you use certain adjuvants like ASO3, ASO4, which will skew the response towards a Th1 type of response. Now, fine. What is the next step? the antigen which has been engulfed by the APC has to go to the draining lymph node. So once the antigen is engulfed by the antigen presenting cell, it forms a vacuole called the phagosome. The phagosome combines with the lysosome, giving rise to a phagolysosome. This contains digestive enzymes which break down the the pathogen which is there in the phagosome, making bits and pieces of it. Those which are important for immunity are presented on the cell surface, whereas those which are not necessary are thrown out by a process called exocytosis. When all this is happening, this antigen presenting cell is gradually moving towards the lymph node, and this migration is induced by certain chemokines. Chemokines are proteins which induce the movement of certain types of cells. And during this transit period, these dendritic cells undergo functional and phenotypical maturation, including upgrading of many of the co-stimulatory molecules, cytokines, etc. Ultimately, it reaches the T cell zone of the lymph node where the antigens are presented to the T cells. So this is the journey of the dendritic cell all along the efferent lymphatics to the T cell zone. So here we should remember that an inactivated vaccine does not multiply within the body. It drains only to the regional lymph node. So you get only local and unilateral lymph node activation. On the other hand, a live vaccine is not retained at the site. It gets disseminated throughout the body. It multiplies everywhere. And there is a multifocal lymph node activation all over the body. So that's why it's not unusual to get generalized lymphadenopathy after you have taken the rubella vaccine. We must also remember that the skin has many layers. The dermis has the maximum number of antigen presenting cells. Muscles have intermediate numbers, whereas the subcutaneous tissue has the least number of antigen presenting cells. So putting together these two facts, live attenuated vaccines multiply. The antigen load is large. So where you administer it is not important. You give subcutaneous or intramuscularly, it's going to work equally well. On the other hand, inactivated vaccines have a much lower antigen load. So it is very essential to administer it only at that place which has a good number of antigen presenting cells. And for convenience and ease of administration, it is generally administered in the muscle. We must remember that if we administer in the dermis, it produces a much better immunological response. But there is a technical difficulty of administering in the dermis. You cannot give adjuvanted vaccines in the dermis. That's the reason we prefer intramuscular and not intradermal vaccination. The other concept you need to understand is this MHC class restriction. Now, what is this MHC? MHC stands for Major Histocompatibility Complex. Now, when you have an intracellular antigen, like a virus particle, broken down virus, that is broken down by the proteosomes. It enters the endoplasmic reticulum, modified, and it is presented to the CD8 plus lymphocyte in relation to a MHC class 1 molecule. On the other hand, if you have an exogenous, something that is circulating in the blood, engulfed by the antigen presenting cells, and ultimately it is presented to CD4 lymphocytes in relation to a MHC class 2 complex. So class 1 CD8 plus, class 2 CD4. Endogenous MHC class 1 CD8. Exogenous MHC class 2 and CD4. Please remember this. So next what happens? It reaches a lymph node. Now within the lymph node, what happens is slightly different between a polysaccharide and a protein antigen. As far as a polysaccharide antigen, the polysaccharide antigen generally need not be taken up by the antigen presenting cells. It reaches the lymph node or the secondary lymphoid structure through the bloodstream, the lymphatics, and reaches the marginal sinus where there are specialized cells, macrophages, to take it up. Once that occurs, this antigen comes into contact with specific B cells which have specific affinity for this particular polysaccharide. Once it meets this specific B cell, these B cells get activated, multiply, and result in production of plasma cells, smaller quantity and producing predominantly IgG and IgG2 and IgM response. So polysaccharide vaccines, so what are the clinical implications for us? Polysaccharide vaccines, low titers of antibodies with poor avidity. They don't have a very strong affinity for the antigen. There is no memory cell response. Children below 2 years cannot use it because the entire immunological process occurs in the B cell zones of the liver and lymph nodes, and these are not well developed till the age of 2 years. And one more problem with polysaccharide antigen is hyporesponsiveness. With every subsequent dose, the response becomes less and less. And why does this happen? Because the B cell zone is not replenished. So every time there is a stimulus, some amount of B cells are used. And there may come a situation where there are no more B cells specific for that particular antigen, and that's the time the vaccine stops working. So hyporesponsiveness. Next, let's look into what happens when a protein antigen reaches the lymph node. Things are very different. Initially, like a polysaccharide antigen, it enters, produces small quantities of IgM type of antibodies. But what is more important is some of these activated B cells, under the influence of these T helper cells, which in turn have been activated by the antigen-bearing dendritic cells, they move towards the T cell zone and establish friendship with what is known as the pre-germinal center T follicular helper cells. This combination then moves towards the T cell zone, giving rise to the germinal center reaction. Now, what is this germinal center reaction? Is from one single B cell clone that is specific for one particular antigen, they undergo a clonal expansion, multiply millions of times, and they also undergo somatic hypermutation. I told you last time in the variable segment of the immunoglobulin, you got to produce a variety of antibodies, so somatic hypermutation occurs. And these cells, which are now known as the centrocytes, move into the light zone. In the centrocyte, these centrocytes pick up antigens which are on these follicular dendritic cells. They internalize it and present it to the T follicular helper cells. The T follicular helper cell decides whether this antibody produced by this particular cell, is it of a very superior quality? Well, if it has of a very good quality, very good affinity, it has passed its exams, it gets the green signal, it goes back here, multiplies again, and moves into the bloodstream either as memory cells or plasma cells, producing large quantities of very specific antibodies with a very, very high affinity. So the primary purpose of the germinal center reaction is, one, production of very highly specific antibodies with very high affinity for a particular antigen. And second, converting an IgM response into IgG response, which is known as isotype switching. Now, what is its significance in our clinical practice? We know that antibody protection takes at least 2 weeks following the onset of the germinal center reaction. So protection by any vaccine dose begins not earlier than 2 weeks after administering the vaccine. So when you want to go on a holiday and you want to take a rabies vaccine, you should finish it at least 2 weeks before. If a child is undergoing splenectomy, you got to finish the vaccine schedule at least 2 weeks before, as far as inactivated, and 4 weeks for the live attenuated vaccine. On the other hand, affinity maturation takes 4 to 6 weeks. Okay. So you need a minimal interval of 4 months between the priming and boosting dose so that there is optimal affinity maturation a large number of memory B cells which sit in the lymph node in the spleen. So to have a very good memory cell response, the primary and the booster dose should be separated by at least 4 to 6 weeks, right? So these are the implications of what this particular stage. Last, we come to generation of the immune memory response. We must remember that once this germinal center reaction has occurred, B memory cells are formed which transiently enter the circulation and go and sit in niches in the bone marrow and the spleen. These B memory cells are quiescent cells. They do not produce antibodies. They're just sitting quietly. Once an antigen exposure occurs again, these B cells very rapidly multiply, becoming plasma cells and produce large quantities of highly specific antibodies. We must remember that the memory cell response does not need a germinal center reaction. So the reaction is very quick. So you get very good antibody titers in a very short time. In 3 to 7 days, you have very high responses following a booster dose. The other implication is these memory cells are really memory cells. They do not forget the encounter with the antigen, which may have occurred a few years ago or a few decades ago. So implication is when you catch up on a incomplete schedule, you never have to restart the schedule again. You just continue the schedule and complete it. We have dealt so far with the B cell. Let us look at the T cell responses. Except polysaccharide vaccines, all vaccines elicit a CD4 response. As far as the inactivated vaccines, it's predominantly CD4, whereas live vaccines elicit both CD4 and 8. The only vaccine which works predominantly on a T cell response is BCG. And the COVID pandemic, we have become very familiar with the concept that while antibodies can reduce infection, it's the T cells which is important for protection against complication and attenuation of the disease, right? So this is the antigen presenting cell which has ingested the antigen. Extracellular antigens are presented to class 2 MHC on the CD4 cells. These CD4 cells have two functions. They help the B cells and they also help the CD8 cells. CD8 cells, which are presented with the MHC class 1 molecule, become CD8 effector cells or CD8 memory cells. Okay. Now, these CD8 effector cells generally exert actions through interferons, or they produce certain proteins called perforins. They punch holes into the organisms. A second group of enzymes called granzymes then disintegrate the organism, and this organism is then phagocytized and thrown out of the body. So this is the function, the way the T cells work in the human body. And I think this is something you have been hearing very often, especially in related to pertussis, TH17, TH1, TH2. So what are all these? TH1 classically produce interferon gamma, and they are responsible for protection against intracellular viral and bacterial pathogens. TH2 predominantly produce IL-4, and they're mainly concerned with allergic immune response to helminthic infection, and some extracellular organisms. TH17 is something that has gained a lot of importance in recent times. The signature cytokine is IL-17. It is mainly dealt with dealing extracellular organisms which have a mucosal site of entry. That's the reason why whole cell pertussis vaccines elicit a strong TH17 response, so it reduces colonization and has a herd effect, whereas acellular do not induce a TH17 response, so they do not reduce nasopharyngeal colonization and does not exert a herd effect. Well, you have a TH22, T follicular, we just said, and to control this entire thing, you have T regulatory cells. So these are the important subsets of T cells, which is worthwhile just keeping it in your mind. Just remember that there are different cells, and main important are TH1, TH2, and TH17 as far as our clinical practice is concerned. We know that polysaccharide and protein antigens elicit different type of responses, which I just mentioned. So what are its implications? So basically, a pure polysaccharide vaccine has low levels, predominantly IgM, no germinal center, weaker antibodies, poorer activity, no booster response, does not affect nasopharyngeal carriage, so no herd effect, and can be used only above the age of 2 years. On the other hand, protein vaccines, which are T cell dependent, have all these advantages. So what is being done? You're tagging on a polysaccharide protein, converting it into a conjugate vaccine, which behaves immunologically like a protein vaccine, but elicits a very, very strong response, antibody response against the polysaccharide that it is carrying. And all of the present day vaccines, take it pertussis, pneumococcal or Hib or meningococcal, these are all protein polysaccharide conjugate vaccines. Now, we dealt with the cellular response. Now, what happens to the antibodies after we give a vaccine? Now, following the first dose of the vaccine, there's a very slow rise of antibodies. This is the extra follicular reaction that is occurring without the germinal cells. And it is purely a IgM, predominantly an IgM response. Once the germinal centers form and starts acting, you get a sudden rise in antibody titers, which are now predominantly IgG. These titers then begin to fall and reach almost baseline levels at 12 weeks. Now, if you see, the peak has occurred just before the end of 4 weeks. Okay. Now, when you give a second a booster is given, as I said, this extra follicular reaction, germinal center reaction is not there. You get a very, very feeble IgM response, but you get a rapid rise in specific IgG antibodies. These antibodies initially have a rapid fall, and then the long-acting plasma cells, which are situated in the bone marrow, they produce antibodies and maintain levels for a long period of time. Okay. So what is the implication? If you keep a minimum interval of 4 weeks, the interference for the subsequent doses is very much less. This interference is even less if the interval is 6 weeks, and even less if it is 8 weeks. That's why USA uses an 8-week interval. They week 2 months, 4 months, 6 months. But in developing countries, the diseases occur so early, we need early protection, so we prefer a 4-week interval vaccine. Now, we must remember that immune memory, as I said, is the most important aspect of any vaccine. And this immune memory depends upon whether what is the incubation period of the infection, what is the quality of the memory cell response, and finally, what is the level of antibodies. I will give you some examples now. Take the example of hepatitis B. It has a long incubation period, 4 to 6 weeks. Once there is exposure to the pathogen, in a vaccinated individual, his antibody titers have fallen very low. Once there's exposure, an anamnestic reaction occurs, which a very rapid rise in antibody titers. This rise in antibody titers reaches the protective levels long before the incubation period of the disease is complete. So in these cases, you don't have to give boosters and don't require persistence of protective antibody titers. So diseases with long incubation period, there is no need for boosters. On the other hand, look at an illness like, say, Hib or a pneumococcal vaccine or a meningococcal disease. Once the titers fall to below protective levels, when you give a booster or there's a re-exposure, the antibody titers, of course, rise very high, but still this rise is occurring at a pace at which the incubation period is already over. So at the end of the incubation period, you still do not have protective antibody titer levels. So in such illnesses, you have to give repeated boosters so that you maintain the antibody titers at the protective level for a long period of time. A third situation is where a viral vaccine. It rises up, it falls, but never falls to a level where protection is not there. And a classical example is yellow fever, which requires only one dose in the entire lifetime, or even the chicken pox and say the rubella vaccine. They give almost lifelong protection. Now we begin vaccination at a very young age. Are there any limitations? Yes, plenty of them. Maternal antibodies are going to inhibit the antibody responses. We all know that you can't give IPV very early, you can't give DPT very early. Whereas live vaccines, you cannot give it almost till the end of the first year. You can't give measles at 6 months or 3 months or 4 months. You can't give chickenpox below 12 months. There is also a lot of immune immaturity. The marginal zones are not well formed. The germinal center response, the complement response, the long-lived plasma cell response, the memory B cell pool, all are suboptimal. Antibody responses are also shorter lasting. The T cell responses are fine. That's why you can give BCG, which is a predominantly T cell vaccine. So what are the implications? When you give vaccine very early, you require multiple priming doses. So take DPT, take PCV, take HIB. First 6 months, you give 3 priming doses. 6 to 12 months, you give 2 priming doses. Above 1 year, only 1 priming dose. Because as the child advances in age, these limitations reduce, the immunological systems become more and more mature and gives rise to much better immune response. Let's now talk something about herd immunity, which has become very popular since the COVID times. Let's get some definitions. Herd immunity is the proportion in a population that is immune. So this can be either because they are protected by the vaccine or they have had the disease and sustained protection. The second concept definition is called herd effect. Herd effect is the reduction of disease among non-vaccinated members when a good proportion of the population is vaccinated. And this is seen only in infection which have a human to human spread and not where there is a zoonotic spread. Okay. Often these two terms are used interchangeably, but there are, again, I said, differences between herd immunity and herd effect. The next thing you need to understand is what is herd immunity threshold. This is the vaccination coverage rate in a population at which disease transmission stops. Theoretically, a disease can be eradicated even if the entire population has not been vaccinated. Let's look at this diagram. Now, the blue are those who are not immunized but healthy. The red are those who are diseased, and the yellow are those who are vaccinated and healthy. In a population who is just not immunized, if there are some infected persons, it spreads very rapidly. In a population which is partially vaccinated, the disease still spreads, though to a lesser extent. But if you have a large population vaccinated, every infected person is met with a defensive wall around it. So it cannot bypass this wall and go and infect a unvaccinated person. So this is the very concept of herd immunity. So herd immunity is necessary when you want to protect someone who cannot take the vaccine. Maybe he's an immunodeficient, maybe he has some allergy to the vaccine. The other thing one should keep in mind is there is a direct relationship between the R0 value, R0 value, and herd immunity threshold. So for diseases which have a low R0 value, the herd immunity threshold is also low. Like mumps has a R of 4 to 7, 75% fine. Other hand, if you take disease like pertussis or measles, which have a very high RO, to recapitulate what is R0, the number of persons that can be secondarily infected by the index case in a population which does not have any immunity against that particular disease. For pertussis, 12 to 17, measles 9 to 18. So here you require 95% coverage in the population to reach herd immunity threshold. As far as COVID is concerned, this herd immunity has been a moving target. What began as 2, 2.5 now went almost to 7 in the Omicron wave. So probably non-existent herd immunity. Now, having dealt with all these basic concepts of immunization and its application, let's come to some important terminologies. Vaccine efficacy, vaccine effective. You're going to come across this term very frequently whenever a new vaccine is introduced. Vaccine efficacy is percentage reduction of disease in a vaccinated group of people compared to an unvaccinated group. This is usually occurs in an ideal condition like a trial. Now, why is this ideal condition? You are having healthy hosts, all have taken the vaccine according to the schedule. The vaccine has been kept properly, proper storage, ideal condition. Vaccine effectiveness is the degree of disease reduction when the vaccine is rolled out in the population. Okay. So vaccine effectiveness is a combination of efficacy, the coverage, programmatic factors, especially cold chain maintenance, and finally herd effect. Now, vaccine effectiveness can be higher than efficacy if there's a very strong herd effect. The 7-valent pneumococcal vaccine caused a greater reduction in pneumococcal invasive disease in the unvaccinated population rather than the vaccinated, a very, very strong herd effect. On the other hand, effectiveness will be much lower than the efficacy if you have a faulty cold chain, so an ineffective vaccine, faulty techniques of giving the vaccine, or poor coverage. To give you a classical example, recently a paper was published about the Navi Mumbai TCV study. And this study showed that at about 70% coverage, the vaccine efficacy was 58%. We all read 80%, 85%. But this was at 78%. If the coverage goes to 90%, then the efficacy will go up to 85%. So lower the coverage, lower will be the vaccine effectiveness. Seroconversion. What is seroconversion? Greater than or equal to 4-fold rise in antibody titers from pre-vaccination to post-vaccination. Or in a situation where there are no antibodies at all in the blood, appearance of detectable antibodies following vaccination is called seroconversion. Seroprotection is an antibody response capable of preventing infection. Okay, that is seroprotection, which is there for many of the vaccines. What is geometric mean titer? You always read GMTs. You don't read single titer values. This is the arithmetic mean of antibody titers in a population elicited by vaccination. So what does it mean? You take 100 people, you add up all their antibody titers, divide it by 100, and that is the arithmetic mean. That is the geometric mean titer. What is vaccine failure? It can be of two types. It can be primary or it can be secondary. What is primary vaccine failure? An individual fails to make an adequate immune response to the initial vaccination. 10% in measles, 5% for mumps, and almost 16% for a single dose varicella vaccine. Now, what is secondary vaccine failure? The individual responded, but after a period of time, the antibody titers wane and he becomes susceptible to infection. So this is called a secondary vaccine, which is a hallmark of all protein vaccines. Now, finally, I would like to introduce a concept of what is known as correlate of protection. Now, what is a correlate of protection? It's a measurable immune response to the vaccine, which is statistically associated with protection against that particular pathogen. We must remember that this correlate is not an absolute value. Correlate of protection for sterilizing immunity will be different from invasive disease. It may be different for different serotypes. Even as far as PCV is concerned, the correlate of protection is different for different serotypes, although we say only 0.35 ml. Okay. There are different types of correlates of protection. One can be absolute. That means you have this value, you're 100% protected. Like anti-HPS greater than 20 international units, you're certain you're not going to get chronic hepatitis B infection. Another is relative, where it may offer protection in the majority of cases. Take the classical example of influenza. What is the correlate of protection? A titer of greater than 1 in 40 of the anti-Hem HI titer indicates a 50% protective ability. So this is a relative. What is a co-correlate? When you have more than 2 correlates of protection, 2 or more, and these 2 or more act either in a synergistic manner or additive manner or independently they may exist. Now, for example, if you take PCV, you have 2 correlates. One is an anti-IgG titer of greater than 0.35 and you have an OPA titer of greater than 1/8. So these are co-correlates. Finally, there is something called the surrogate. What is a surrogate? It's again a quantified specific immune response that is in itself not protective, but it substitutes for some other correlate which is known or unknown. Can I get it? You have got a specific immune response which correlates with protection, which correlates with some other parameter, which you know or do not know. Now, for example, for rotavirus vaccine, we say a serum anti-rotavirus Ig of greater than 20 is a surrogate for protection because the serum IgA does not protect. It is a secretory IgA in the intestine which protects. Okay. We know that they're related, but there is no absolute correlation between those. So it's a surrogate. So friends, I think this sort of covers up, I think, almost the entire concept of an introduction to vaccinology as is relevant for clinical practice. Well, if there are any further questions, I'll be very, very happy to answer whatever I can. Thank you very much.
Thank you so much, Kashisa. That was a really, really interesting class. The slides, everything was excellent. And I think there won't be any better way to inaugurate this program. So I request the participants to raise your questions or doubts if you have any. And I think you can switch on your video and audio and ask the questions directly. That will be better.
There is a questionnaire which says trained innate immunity, slight confusion. Dr. Rajkumar Goel, can you come on and say what is the confusion?
Yes, sir. Good evening, sir.
Good evening.
Yes, sir. Thank you, sir, for this nice presentation. Sir, the confusion is that in innate immunity, we usually take it as the body is already having from our natural lymphocyte macrophage.
Yes.
And adaptive, we all know. But I did not understand the whole concept of trained innate immunity. Is it really helpful for some adaptive immunity? Or it is...
Now, trained innate immunity, of course, adaptive innate immunity is definitely helpful for adaptive immunity. Now, trained innate immunity was a concept which has been known for a very long time. See, it has been very well known, especially with BCG vaccine, that BCG reduced neonatal mortality. It reduced the incidence of all-cause respiratory tract infections, hospitalization in the first 6 to 12 months of life. Okay, and that is because of this trained innate immunity. What happens is with this viral vaccines, once the first dose of the vaccine is given, okay, there are changes which occur in the genetic response to subsequent exposures. So if you get a level of cytokine X level, when there is re-exposure, it may be 2x or 3x or 4x. You do not expect this in an innate immune response. The definition of innate immune response is the response is almost the same every time that exposure occurs. So there is a sort of a remodeling or a retraining of the immune cells, whereby there is a heightened response to a subsequent exposure of the same pathogen or even any unrelated pathogen. You give BCG, it gives you protection against tuberculosis, it gives you protection against RSV, it gives you protection against pneumococcal infections, unrelated infection. This is the concept of trained innate immunity. You must remember that even innate immunity, we are born with it, but the innate immunity to become active, exposure has to occur. So you get a certain level with the first exposure. With the second and subsequent exposure, the levels are even better. This is the concept of train, and that's the reason why there was a rush to take BCG and MMR when the COVID pandemic first began. Of course, now no one is interested because we have directly we have COVID vaccines.
Thank you, sir.
Kasi sir.
Yes. Your voice is breaking a lot.
Am I audible now?
Yes, yes, yes.
So what are these macrophages, plasma cell, mast cell? All these are B cells, and what is tissue specific macrophage?
No.
Whether it is a further graduation of these B cells into particular tissue or like that?
No. You have antigen presenting cells, which are basically dendritic cells, macrophages, mast cells, and natural killer cells. These are the 4 types of antigen presenting cells. Some are circulating, like your dendritic cell. Some are fixed, like the mast cells. They are fixed in the tissues. But once antigen exposure occurs, they enter the circulation. So innate immune response cells are different. B cells also are operative in an innate immune response, but phylogenetically, structurally, they are in no way related to your macrophages or monocytes or even your antigen presenting, other antigen presenting cells. B cells are a different class apart. Did this answer your question?
No, sir.
Tell me.
So these macrophages are not monocytes?
It is a macrophage monocyte complex. I'm almost interchangeable. One can get converted into the other after exposure to antigen.
And plasma
monocyte is fixed. Once it enters the circulation, it becomes a macrophage.
And this plasma cell is again a specialized
plasma cell is a B cell actively producing large quantities of high affinity antibody. That is a plasma cell. Plasma cells can be short-lived. Plasma cells can be long-lived. Long-lived plasma cells go to the bone marrow niches and keep producing antibodies for a long period of time. That is what sustains your antibody titers till you give the next dose of the booster.
And whether mast cell come into circulation?
Mast cells are fixed. Once antigen exposure occurs, it gets converted to a macrophage and that enters the circulation.
Thank you, sir.
Okay.
Sir, I am Dr. Hari Kumar. Sir, I have a question regarding polysaccharides and conjugate polysaccharide vaccines.
Yes.
So, polysaccharide vaccines have its own limitation, like cannot be used below 2 years and all. But still, polysaccharide vaccines like pneumo-23 are still used. Why polysaccharide vaccines are still used?
Now, generally, you don't use polysaccharide vaccines when you have a corresponding protein conjugate vaccine, because it's far superior. You must remember that as far as pneumococcal infection is concerned, the priming is done with a conjugate vaccine, always, at all ages. Why do you need to give a polysaccharide vaccine after that? Your PCV13 has only 13 serotypes. Your pneumo-23 has 23 serotypes. So to broaden the protection, you are giving a polysaccharide. You never do that for Hib. You never do that for meningococcal because they are all single serotypes. Okay, you do that only for the pneumococcal. So there's no sense in using a polysaccharide when you have a protein polysaccharide vaccine, except for pneumococcal infections.
Thank you. Thank you, sir.
Thank you.
There is one more question in the chat box.
Sir,
Yeah, Dr. Keshulo.
So once again, excellent talk as usual by
you.
Dr. Kasi sir, because I am hearing to you since almost 3 decades. Sir, I want you to throw some light on again the difference between polysaccharide and protein vaccine, please.
Okay, fine. I think, see, polysaccharide vaccines are called T-cell independent vaccines. They don't require cooperation of the T cells to elicit an immune response. So the end result is there is no germinal center reaction with T-cell independent vaccines like a polysaccharide vaccines. So no germinal center means no affinity maturation, no class switch. So you get predominantly IgM response, you get low levels of antibody titers, which are short lasting. When you attach that polysaccharide to a protein, the body's immune system is tricked into believing that it is actually a protein vaccines. So it undergoes a germinal center reaction, produces plasma cells, produces memory cells and high titers of antibodies. See, what is very intriguing is, you have a T cell antigen in the protein and you have polysaccharide. Okay. Now your B cells are producing anti-polysaccharide antibodies, but the T cell recognizes only the protein. It does not recognize the polysaccharide. Clear? So most of the protein conjugate vaccines, polysaccharide conjugate vaccines, work only on basis of humoral immunity and not T cell immunity. However, most of these vaccines are targeting extracellular organisms, and that is the reason why these vaccines have become so successful. If it was an intracellular organism, the protein saccharide would not have worked. Conjugate vaccine would not have worked.
Okay.
Clear?
Yes, sir. Yes.
Yes.
Sir, very fantastic talk as usual.
Thank you.
Sir, can you enumerate again the surrogate protection?
Pardon?
Surrogate protection, as you last
Surrogate.
Okay.
Surrogate.
Okay, I'll tell you.
Surrogate protection, please.
Now, there are certain diseases where we know that a vaccine works, but we are not sure which is the immunological parameter which correlates for protection. Like, is it the IgG titers? Is it something in the T cells? What is it? We do not know. Now, I gave the example of rotavirus vaccine. Rotavirus vaccine is basically a mucosal infection. So anything that is there in the blood cannot confer protection. So it is a secretory IgA in the intestines which gives protection against rotavirus infection. Technically, very difficult to measure the secretory IgA. But we know that there is some correlation between the secretory IgA in the intestines and the IgA in the blood, the IgA in the blood, the total IgA in the blood. So in this case, the total IgA in the blood, the serum IgA, is taken as a surrogate for the secretory IgA and says that probably a level of about 20 international units is a surrogate of protection. It's not a correlate. Clear? So this is the concept of surrogate.
Excuse me, sir.
Yes, sir.
Sir, this is Dr. Ashwini. Sir, I
Yeah.
just wanted to the lectures. I joined a little late, sir. Though, but the material that had been given to read in that, what I came across was B memory cells. T memory cells, I can understand well. What is the role of B memory cells and how do they differ from the T memory cells?
Now see, the B memory cells are concerned with antibody production. The T memory cells are concerned with the T cell response, CD4, CD8 cell responses. Both are important for protection. Antibodies are especially important when you want to prevent infection. T cell responses when you want to prevent complications or severity of the infection. Okay. So just as the way your B memory cells are produced from the germinal follicles and they escape into the circulation and then they go and lodge themselves in the spleen and bone marrow, the same way the T memory cells also are formed, which again go and sit in the same niches, and they also exhibit an anamnestic response when there is a re-exposure. So when there's a re-exposure, you get heightened IgG, you also get heightened response to the T cell response or the cell-mediated immune response. They go almost parallel, hand in hand. Each has their own function.
Sir, so in case of polysaccharide vaccines, the B memory cells are not stimulated because...
Yes, there is no germinal center reaction.
Okay.
There is no germinal center reaction.
So B memory cells also require the help of T cells to
yes,
form.
T cells are crucial for production of the germinal center. See, it is the B cell going and meeting a T cell which initiates the germinal center reaction. Even sustenance, affinity maturation, everything you require a T cell. So if you don't have T cells, you're going to get a very, very poor immunological reaction. Now I'm going to take the case of measles, Now you can have someone who has agomaglobulinemia will suffer from measles but will not die of measles. But someone who has a T cell defect will die of measles because you cannot prevent severe infection. So both are important.
Thank you, sir. Thank you.
Thank you. Yes, Dr. Alokji.
Wonderful talk, sir.
Thank you.
This is regarding a confusion in the schedule of rabies vaccine, which most of us are really confused whether to follow the WHO IAP recommendations or the NCDC recommendations in the pre-exposure and the post-exposure prophylaxis. It's a one-dose sparing schedule between what the government of India recommends till now and what IAP has adopted the WHO recommendations.
Okay, sir.
So,
yeah, I will just, yes.
Is, if we are using a 2-dose schedule in a pre-exposure prophylaxis 07, and the bite occurs on the 8th day,
yeah,
will that be a pre-exposure prophylaxis or we need to convert it to a post-exposure prophylaxis?
Okay. Now, I think one of the concepts which I just said, it takes at least 2 weeks after that antigen is administered to have a protective immune response. So before that, protection is, probably not adequate. You're not sure of that particular protection. Now, coming to the first question, which should we follow? Why did this 5-dose become 4-dose? See, in a 5-dose schedule, the first 3 are priming, 4th and 5th are boosting. In a 4-dose schedule, the first 3 remain priming, but you have only 1 boosting. Why did they reduce it? Because they found that between the 4th and the 5th dose, the rise in antibody titers was very minimal. Okay. You give 4 doses and measure the antibody titers. You give 5 doses and measure the antibody titers. The difference was not much. So that 5th, the second booster was sort of really not necessary. Not only that, subsequently studies, observational studies have shown that children who received or adults or subjects who received only 4 doses were adequately protected against measles, against rabies. And much of these studies have come from India also. I mean, if you see the WHO position paper and the, the background material, quite a few, references from Indian studies. So from the immunological point of view, if you use the WHO schedule, you're perfectly right. No problem, sir. Now, why should I still look at the NCDC schedule? Rabies is a disease which is uniformly fatal. Okay. It is also a disease where even when you do everything, failures can occur. I think Kerala reports have come. Recently also there's been a report of failure of a good post-exposure prophylaxis. So in such cases, if legal issues arise, the court will generally consider the nationally recommended schedule rather than some other schedule. It is only from that point of view that this disparity is there. From an immunological point, your WHO 4-dose schedule is perfectly fine. The DCGI has not adopted it because they want adequate studies from India to approve that abbreviated schedule. I think it's a matter of time before the government may agree for it also.
Thank you. Thank you, sir.
Thank you.
Hello, sir. Good evening.
Yes.
Sir, I'm Dr. Azhar from Kerala.
Yes, sir.
In certain parts of Kerala, we are getting measles outbreak. And we are getting young infants with 6 months or 7 months with measles. And those kids with 1 dose of MR also getting measles with pneumonia also. So is it recommended to give MR at early stage and cut short the 2nd dose of MR at earlier age?
Any measles vaccine given before the age of 12 months should be considered as an invalid dose. Okay. In case of an epidemic or an outbreak, you can give as early as 6 months, but giving before 6 months is a waste because your seroconversion will be less than 50%. Okay. Even if you give at 6 months, it is somewhere around 60%. At 9 months, it is about 85%. Only above 1 year, it goes over 95%. So if you give a vaccine before 1 year, as I said, why do you want to give the vaccine? You want to give the vaccine because you don't want the child to die of complications. And that T cell response is not affected by circulating antibodies. You got it? So even if you give at 6 months, it may not prevent measles, but it will prevent the child from dying of measles because of the T cell response. So there is a recommendation to give vaccine even as early as 6 months. but you consider that as an invalid dose, and then you give again at 9 months and 15 to 18 months as it is there in our NIP. So you're giving it for the T cell response, not for the antibody. It will not prevent, but it will prevent death due to measles or complications due to measles, generally.
And sir, what about the second dose giving at early stage?
Now, as I said, in developing countries, measles occurs very early in life. That is why we do not have the luxury of waiting till 12 months to give the first dose of measles. We have to give at 9 months. We know that the vaccine induces suboptimal response, so we are giving a second dose. Now, all viral vaccines, live viral vaccines, theoretically should work with one dose. Why are we giving the second dose? Two reasons. One is immunological reason because of primary vaccine failure. For measles, given at 9 months, primary vaccine failure is 15%. Given about 12 to 15 months, it hardly comes to 5%. Mumps primary vaccine failure is about 5%. Rubella, it is only 1%. Chickenpox with one dose, 16%. So because of the primary vaccine failure, you're giving the second. The second is programmatic reasons. Suppose there is a campaign for measles. Someone has missed it. Logistically, it is easier to give everyone the second dose rather than going and trying to find out who has not received a second dose. So you give everyone a second dose. So immunological reasons and programmatic issues, why you give a second dose.
But we are giving 3 doses of MMR, sir.
Three doses we are giving because mumps, the antibody titers wane with time. So after giving the 15 to 18 months, the titers at 5 to 6 years is low. In the government schedule, we don't give that. We don't give months because, see, mumps is not a public health issue. It does not kill. It does not lead to hospitalization generally. So for the government, it is not a priority issue. Okay, that's the reason mumps is not there. The mumps antibody titers every 7 years falls by at least about 40%. In fact, even in the American Academy, there's a recommendation that those who have received a 5-year MMR, if there is an outbreak in the adolescent age group, they should receive one additional dose. Right? Someone wants some explanation about TH1 action, Dr. Sangeeta. Whole cell and acellular. Okay, there's a question. Could you explain again the TH1 action with respect to whole cell and acellular vaccine and how it
TH17.
affects TH17. See, there are 3 TH subtypes important as far as pertussis is concerned: TH1, TH2, and TH17. Okay. TH1 is important for cell-mediated intracellular organisms. Pertussis is more of an extracellular organism, though it also has an intracellular phase. Now, a whole cell vaccine, because it contains many things like lipopolysaccharides, etc., induces a very strong innate immune response. That's the reason why you get more of fever, pain, swelling with whole cell vaccine. Once you have a stronger whole cell innate immune response, the response is skewed towards a TH1, TH17. Okay. As I said earlier, TH17 is important for extracellular organisms which have a mucosal route of entry. Not just pertussis, pneumococcus, many other infections which have a mucosal route of entry. So if you have a robust TH17 response, you have T cells and antibody cytokines sitting there preventing the germ from colonizing the mucosa. So you get sterilizing immunity, and sterilizing immunity is going to give rise to herd effect. Acellular pertussis vaccine, because it is highly purified, does not contain the lipopolysaccharide and many other constituents of the entire bordetella pertussis, elicits, and because it has alum as a preservative, it elicits predominantly a TH2 and a very little of TH1 and TH17. So if you look at the antibody titers, acellular gives higher antibody titers compared to whole cell. Okay. If you look at the protective efficacies in the first few years of vaccination, both give similar antibody, gives similar protection. But if you look at the long-term protection, whole cell is far, far superior. In fact, They have done a study where they have taken two groups, one who received all whole cell and the other one who received all acellular priming doses. They have given repeated doses of Tdap or acellular boosters. And what they have found that even 17 to 23 years later, the memory B cell response is far more robust and superior qualitatively and quantitatively when in those who are primed with the whole cell, indicating that there is some sort of imprinting of the immunological memory, skewing it towards a better immunological response. And this imprinting lasts almost a lifetime. Okay. So TH17 will reduce nasopharyngeal colonization and exert a herd effect. This cannot be done with a TH2 or TH1 response.
One question on rotavirus vaccine, sir.
Why rota vaccine is not recommended and interchangeable? I did not understand the first part. Can Dr. Ashwani just come up and reframe the question?
I think he meant why the interchangeability of brands is not recommended.
Okay, now basically, as a general principle, we say avoid interchangeability as much as possible because no one has really studied the interchangeability. But there is definite interchangeability between Rota-Rix and Rota-Tech. There has been a study in USA. And in India, there has been a study of interchangeability of Rota-Vac and Rota-Sil. And it has shown that as long as you give 3 rotavirus vaccines, the immune response is the same. So interchangeability is, I won't say permitted, but interchangeability will not affect the final response. So you can definitely, I mean, if you are not sure which was the previous dose, or you don't have that particular vaccine in your stock on that particular day, give whatever you have. We can't say the same about Rota-Rix, Rota-Tech and Rota-Vac. Can it be interchanged? We don't know. But Rota-Vac, Rota-Sil, yes. Rota-Rix, Rota-Tech, yes. You can interchange them. Now, Dr. Alokji, you have asked about mucosal pertussis vaccine. Yes, there is one mucosal pertussis vaccine called BPZE1. This is a mucosal, live attenuated mucosal vaccine, which has completed phase 1 trial and which is in a very, very positive phase 1 trial, and it has now entered phase 2 trial. And this is a vaccine which everyone is looking at because this is a vaccine which is expected to give sterilizing immunity and not just disease protection. So I think this is something which the whole world will be, waiting for. Now, should rotavirus vaccine, I think we are getting about specific vaccines. Anyway, I'll take it up. Should rota be given even if, yes, you have to be given because we said there are so many serotypes of rotavirus. And your 2 doses or 3 doses is going to give heterotypic protection against all the serotypes. And when you get infection in one serotype, it gives a temporary heterotypic protection, but will not give very good protection with the second infection. Maybe after 2, yes. So if you have had 1 infection with rotaviral diarrhea, it's still worthwhile taking the vaccine. But if you had 2 infections, maybe you have got protection as good as taking the vaccine.
Sir, one more question regarding varicella vaccine.
Yes.
Suppose if a child got infected below the age of 1 year, or still he has to take that varicella vaccine above 15 months?
No. Once you have had the infection, proven varicella infection, either it should be a physician documented varicella or a immunologically lab proved varicella, you don't have to give the vaccine again. There is no need. The only problem with vaccine varicella in the first year of life is you may land up with herpes very early in life. By 8 years, 10 years, you may be susceptible to develop herpes. Otherwise, no vaccine necessary. Dr. Ramakant, you had something?
Yes, sir. I have got 2 questions. One is questioning that why the hyperresponsiveness because of vaccine.
No, your voice is breaking, Dr. Ramakant.
Am I audible now, sir?
Yeah.
Why there is hyporesponsiveness after polysaccharide vaccine? And second question is how we can stop the chase of different serotypes in pneumococcal vaccine and like that?
Okay, now regarding I just mentioned that in my talk. See, polysaccharide vaccines act directly on the B cell follicles in the spleen. Okay. Now, with every exposure, certain amount of B cells are used up. Okay. Now, because there is no germinal center reaction, this B cell pool is not replenished. So after some time, your B cell pool is gone in the spleen and the vaccine will not work. That is the mechanism of action of hyporesponsiveness. This will never occur with a protein vaccine. Right? Got it. Now your second question. Yeah.
So, sir, in this question only, if it is a hyporesponsiveness, then why we are worried about not giving third dose of polysaccharide vaccine?
It will not work. It will not work.
Is it injurious or it will not work?
No, it will not work.
Okay.
You will have a false sense of security that you have given the vaccine, but it will not be working. So in crucial situations, it may make a difference between life and death.
Okay. Second question was,
yeah.
How can we stop the chasing of these different serotypes like in
See, actually now we all know PCV 15 by Merck, now PCV 20 by Pfizer. How many can we go? You must remember that with every additional serotype, the antibody response becomes less and less. PCV 7 had the highest response. PCV 13 response was little less for the common serotypes of PCV 7. PCV 20 is even less. So you cannot go beyond a certain level. The only answer is if you get against a conserved protein, and lot of work is being, and basically is one called histidine triad protein, which is now reaching phase 2 trials. Well, if that comes, we may have a pan-serotype pneumococcal vaccine then. Dr. Keshulu, yes.
Sir. So regarding varicella, of late now we are seeing a lot of varicella cases. There we are seeing cases less than 1 year. Actually, the scheduled dose, first dose is 15 months. So in a child who is getting at a very younger age, so after hearing to you, there is no need to give any dose of vaccine.
Definitely not give the vaccine. And varicella you can give from 12 months onwards if it is necessary, but not before 12 months.
Okay. So one more question. What about this latest RZV, that recombinant zoster vaccine?
I think we are covering all vaccines also. Anyway, just a brief this thing. This is called a recombinant zoster vaccine. The other vaccine which was available was a zoster vaccine live. Recombinant zoster vaccine obviously can be used in immunocompromised, whereas that vaccine you couldn't use. As far as the live vaccine was concerned of MSD, the protective efficacy was at best about 66%, and by the end of 3 years, it almost came down to 0. Protective efficacy was far inferior in the older age group who really need the protection. RZV, on the other hand, has given sustained 90% plus protection until the end of 7 years. It is equally effective in all the age groups. So from that point of view, now the AAP, American Academy of Pediatrics, has recommended preferentially the RZV, and even those who have taken the zoster vaccine live should take 1 dose of RZV at least 8 weeks after the last dose of RZV, live zoster vaccine. And I think RZV is going to come in our country in a couple of months. GSK is going to start marketing, and I think all of us who are above 50 should take that vaccine.
Okay. Thank you,
sir. Kashish sir, questions,
yes, sir.
Doubts regarding the individual vaccines will be.
Yeah, I think individual chapters we can take it.
Yeah. Every vaccine will be discussed later.
Yes, so, fine. So, sir,
Dr.
so
Ashwini,
I think
asked last one question. Dr. Ashwini, I think.
Yeah.
So best route for any vaccine is to use last question.
Yes, I think it's a very, very interesting question. This is what entire research in vaccinology is progressing. Induce sterilizing immunity. Induce sterilizing immunity and not just protective immunity in the serum. See, when you have sterilizing immunity, the bug just cannot enter your system at all. So that is, as I said, pertussis vaccine. your influenza vaccine. Measles vaccine has been tried by the aerosol route, but because of logistic issues, it has not succeeded well. So what happens is when you give through the mucosal route, you're not going to get very high antibody titers in your serum, but you're going to get very high secretory IgA levels, and that is going to prevent colonization. So ultimately, when you use nasal vaccines, when you use oral vaccines, administration is going to become so easy. You don't have to come to a doctor. I mean, they can just buy it and take it in their own house. That's what many people were doing with the intranasal flu vaccine. They were taking it on their own. So ultimately, I think all research is going towards mucosal vaccines now. In fact, even IPV is being adjuvanted with DMLT, double mutant lethal toxin of E. coli, so that IPV starts introducing mucosal immunity, which now IPV does not do. So I think mucosal vaccines are really the vaccines of the future.
Thank you, sir.
Okay,
sir?
That's it. It's almost 10:30. Yes.
Yeah, that was a really, really useful session, sir. Everybody really enjoyed
Whole night will not be enough, sir. Whole night will not be enough.
Thank you.
Once again, thank you so much, sir.
Thank you.
So we will conclude the session for today, sir. And so I will announce for next week.
Sir, Krishnamohan, sir.
Yeah.
Are you?
Yes,
Krishnamohan,
yes,
sir.
Tell me, sir.
Are you going to keep this video?
Yeah, video will be there. We won't be put in the group. I will do the needful for that. It has been recorded. Okay. So regarding the next week, on April 14, we'll be having a talk on polio vaccines by Dr. Dhanya Dharmabalan Madam, Apollo Hospitals. So I will share the link soon, and also some reading materials also. So thank you so much. The link is
going to be shared with all the faculty also, I hope.
Sure, sir. Sure, sir.
Yes.
I will be following another book. Thank you so much.
Thank you very much. It's been a pleasure to talk in the first session. Thank you all.
Good night.
Thank you.
Good night.
Good night.
Thank you.